technology people. So I'd like to talk about how Haskell is tackling the multicore problem. Does anybody not know what I mean by the multicore problem, first of all? So I don't have to explain that. There's often a slide at the beginning of these talks that says, oh, multicore problem. Right, so there's really a two-pronged approach that we're taking to the multicore problem. We're building lots of programming models to make it easy to make parallel programs. And we're building a runtime system that underlies all this stuff and makes it work smoothly on a parallel computer. So I've been spending a lot of my time building the runtime system. That's what I'm really interested in. I've been spending a lot of time doing engineering and so on. But I think the programming models are equally important, and that's what you as a programmer will see. So by the way, feel free to stop me at any point and ask questions. I'm very happy to go off-piste a little, answer questions. So the premise, I suppose, of the programming models in Haskell is that there's no silver bullet, there's no one single programming model that you can use to solve all of your parallel programming problems. So whereas in many languages you'll probably get an emphasis on one particular programming model, like Actors or CSP or something like that, in Haskell we'll give you a range of programming models that will suit different problems. And we're trading off things like robustness, like the guarantees that the programmer will get, speed and the explicitness, the amount of detail the programmer has to give in the program. So these things all sort of trade off against each other. We're trying to give you the right tool for the job, and very often problems come along where we don't have a tool yet. That's where Haskell's sort of flexibility and abstraction really pay off, because we can build new tools on top of the existing infrastructure that we've got. So we usually call these DSLs, domain-specific languages, which is a bit of a sort of grand term for something that's very simple. It's just a library, usually in Haskell, that gives you a set of combinators that you can compose together to make to program a parallel algorithm. So we've got a few examples of that, and I'll explain a little bit about the hard one shortly. But some of these programming models really do need you to get down into the compiler or into the runtime system for reasons of performance to implement them. So we've got a few of those: software transactional memory and those parallel Haskell. So I'm not going to be able to go into much detail about all of these today. I'm going to dive down into a couple of them, but and hopefully give you a flavour for what's there. The main philosophy is that we try to keep the core as small as possible. Okay, so we try to put minimal built-in functionality into Haskell and build everything as libraries and DSLs on top of that. So of course, with all these programming models, that means the programmer's life is a bit more difficult, and they've got to deal with all this complexity and figure out which of the programming models to use. So what we try and do is tell a fairly clear story about which direction you should go. So the main thing we do, first of all, is to tell you the difference between parallelism and concurrency. So this is quite an important distinction, which you don't come across in any programming language, but it's very clear in Haskell. So when I say parallelism, what I'm talking about is using multiple cores for reasons of performance. So you're running a program on your multi-core computer or many computers on a network, perhaps, hoping to get more performance. That's the only reason that you're doing it. Whereas concurrency is a slightly different idea. It's a program instruction technique where you're trying to write a program that does lots of things at the same time. And typically we use threads for doing that. So concurrency is about programming with threads, whereas parallelism is about programming for performance. So our programming models are divided into two. We've got parallel Haskell, several programming models over there, concurrent Haskell, which is just threads, and then there's things like transaction memory and so on top of that. But I'm not going to talk today about concurrent Haskell. It's a really great programming model if that's what you want to do. We have some really nice abstractions there, but today I'm particularly going to focus on parallel Haskell. When I say, so concurrencies, I said it's about appearing to do several things at the same time. For example, a server responding to multiple clients, or if there's a GUI on top of a program and it's doing the computation at the same time, the user can use the GUI while the program is doing its computation. Or you might be downloading multiple web pages and that sort of thing. All of these are examples of concurrent programs that appear to do things at the same time. They're not really doing things at the same time. So you can run these things on top of a single core processor and just switch between different tasks. Or you can write the whole thing as a big event loop. So at the core of the program can be some logic that just says, what's the next thing to do, act on that, and then go back into the loop and see what the next thing is. But that's a really painful and non-modular way to program, so we prefer to use threads instead. And if you have a threaded program running on a multicore, then it does go faster. And indeed, you can use that to write parallel programs. But the big problem with doing that, of course, is that concurrent programming is non-deterministic. You've got these multiple threads all doing side effects at the same time, or having some interaction with the real world. And the order in which they interleave gives non-deterministic results. So we don't like programming with non-determinism because it means that your program does different things depending on the particular environment in which it's running. So it might be a different thing on Fridays, it might be different on the client machine, and so on. It's very hard to debug and test these programs because you can't be sure of eliminating all the possibilities. So our basic thesis in Haskell is that if you don't need non-determinism, you really shouldn't be programming with it. So you should be programming models that give you determinism. And when you're writing a parallel program, very often you don't need non-determinism because you're doing something like matrix multiplication, for example, which always gives the same results. You'd be very surprised if you get a different result on Friday. So our parallel programming models in Haskell are always deterministic. They give you the same answer, you don't have to worry about race conditions and deadlocks. And it means that the programmer can take their existing sequential program that they've debugged and they made sure it worked, and add some parallelism without breaking the program. Okay, so I'm going to introduce one of the programming models that we've got. So at this point I'm doing some Haskell programming. If this is very unfamiliar to you and you get completely lost, please feel free to shout and tell me which bits are confusing. So par is what we call a monad. So a monad you should think of as a computation that you can just sequence things inside of. And there's an operation called run par, which takes a computation in the par monad and returns its value. So a par A is a par computation that returns a value of type A. And if you apply run par to that thing, it gives you the value after doing the computation. So the idea of a par computation is that it's going to be expressing some parallelism and then delivering the result at the end. So the way you get parallelism in par is by using the fork operation, and that takes a par computation, and it is a par computation itself. So that creates a new parallel task, if you like. And these parallel tasks communicate with each other by passing values. And they pass values inside things called IVARs. So it's a historical name, don't worry about it. But an IVAR is, you can think of as a box that just starts off empty and eventually contains a value, but its value never changes once it's been filled. Okay, so you can create a new one of these IVARs. You can get the value from an IVAR, and that waits until the box is full, and then delivers the result. And you can put a value, given an IVAR and a value, that puts the value into the box. Okay, so that's the whole of the API I've just shown you there. Everything else is built on top of these few operations. So, to give you an example of how it works, this small code fragment here does, first of all, it creates a new IVAR and calls it V. Then it forks a new computation. Here is the thing that it forks. It forks a computation that puts into V the value of the function f applied to x. Okay, so inside the forked computation it's computing f applied to x and then putting the result into the V IVAR. And meanwhile, back in the main thread, we're getting the value from the IVAR. So you can think of this as constructing this structure over here. It's a bit like a graph. So the thing that we forked is this blob down here. So this blob does f of x and then puts the result into V. And the main blob up here gets the result, which I showed as an edge, like that. So if we make it slightly more complex, we have two blobs. So now forking first blob that does f of x, and the second blob that does g of x. And then back in the main one, we're doing getting the value from V1, getting the value from V2, and summing them. So this creates a graph that looks like this. And you can see because there are no dependencies between this part over here and this part over here, they can be running parallel. And that's exactly what the runtime or the library will do if you write this program. You don't have to say explicitly that you want to run f of x and g of x in parallel. The very fact that there are no dependencies between them means that they can run in parallel. And they will do if there are multiple cores available. So what we're writing here is a data flow graph. Okay, so you're creating the nodes in the graph by doing fork, and creating the data flow at the edges between them by doing get and put. And you can create any shape of graph that you like. It can even be dynamic. It depends on a graph that depends on the value of certain results that happen during the computation. And the system underneath will schedule that graph across the processes that we've got. So I'll give you a quick example of this. This is one I often use to teach parallel programming. So the example is solving Sudoku problems. I'm not going to parallelize the solving of the problems themselves. It's just an example of a task that takes some time that I'm going to run over multiple data sets to parallelize the action of running that computation over multiple data sets. So this is the whole program, apart from the solver, which is in a separate module. So it has a command line argument, which is the file that we're going to read that has all the data in it. And we read that file into a variable str, and then separate the context of the file into lines. I made a slight mistake, I shouldn't say map there. It should just say lines str. So that separates the file into lines, where each line is a single data set that we're going to solve. And that gives us a list of problems. And then the solutions to those problems just we get by doing map of the solver over the list of problems. So that's mapping the solving function over each of the problems, and that returns maybe a grid. So maybe is the type that's either nothing, if it contains no value, or just as a value. And nothing indicates there's no solution, or just as if there's a solution. And then finally, we filter the list of solutions to just the ones that had solutions. Take the length of that and then print it out. So the idea is just to force all this computation to happen by making sure all the solutions had solutions and then taking the length and then printing it out. Okay, so how are we going to parallelize this problem? Well, first of all, let's run it. So this is an example of the stats that you get when you run a program in Haskell. There's a special option that says give you all the stats, and it tells you how long it took to run it. So in this case it was 3.06 seconds, running on a sample set of 1,000 problems. So to parallelize this problem, I'm going to use the pattern that I showed on a couple of slides ago, where we have two independent computations that we fork in the Parallel mode. So here are the two forks here. And in order to divide the problems into two, I had to split this list. So this line here splits the list of problems at its length divided by 2. So it's just splitting the list into half, giving you two lists, A's and B's. And then we solve A's in one of these forks and solve B's in the other fork. And when we get the results, then we append the two lists together to get the complete list of solutions. So this hopefully is going to parallelize the program so that we run the solutions for each half of the list at the same time. And indeed, if you run it and look at the elapsed time, sure enough, it says 1.99 seconds instead of 3.46 seconds. So it's not running twice as fast as you might expect. So why is that? Well, you can look at what's going on using this tool that we've got called ThreadScope. So ThreadScope tells you something about what was going on in the program when it was run. And this is a typical view that you might expect from running the previous program. So we've got several bars here. The two bars at the bottom correspond to the two processes that we ran it on. So HEC0 and HEC1. So I'll come on to what HEC means later on, but you should think of it as a core. So HEC0 was running, the green bar means it was running up to there, and then HEC1 was running all the way to the end of the program. There was a period at the end here where we only had work on one processor. So it was parallel on two processors all the way up to here, and then it dropped down to one processor to finish off. So that's why we didn't get full parallelism in this example. So it turns out that one half of that list had some problems that were much harder to solve than the other half of it. So even though we divided the list into half, it didn't fully parallelize the problem. So to solve this, to get better parallelism, what we want to do is create fine-grained tasks in the program. So I'm going to show you how to do that. First of all, I'll create a function called spawn, So this is just going to be a helper function. Spawn takes a parallel computation and it forks it off as a parallel task and returns at the same time the IVAR that it can use to get the result later on. So this is just packaging up a bit of the stuff that we did before, getting a new IVAR, forking the computation, putting its result into the IVAR, and meanwhile returning the IVAR to get the result later on. So we can use spawn to make a function called parmap. So parmap is a very common thing that's used in parallel programming. It applies a function in parallel to all the elements of the list and then returns the units of results. So to program parmap, what we can do is, well, I'm not going to go into great detail about how this works, but it's mapping spawn over the original list. And in each of those, for each element we're going to apply the function if and then spawn that as a parallel task. Getting back a list of IVARs, and then once we've spawned all those tasks, we can wait for all the results by mapping get over the list of IVARs that we've got. Okay? So this creates, if you think of the data flow graph that it's creating something like this, a bunch of blobs doing computation that each of which are going to put their results back into the IVAR, and then the main blob down here is going to get all the results. It's a very simple sort of master-slave type arrangement. And we can plug that back into the original program, just in place of the original map that we had, replace that with run power of parmap. And indeed that parallelizes the problem quite nicely. So now we're getting closer to a factor of 2 speed up, whereas previously we had more like 1.5. And indeed you can run this on 8 cores as well, whereas previously when we were dividing the problem into 2, we only run it on 2 cores. So now we can run it on 8 cores with even more cores, and in this case it gets up to 5.9 speed. So that's quite nice. So the important thing is that the programmer is not saying how many cores they want to run it on when they write the program, they're just saying, here is what you can do in parallel if you want to. And the underlying system is scheduling that work across the cores. So this diagram shows what the program looks like, what the new program looks like, running in parallel all the way to the end. So you might say, well, why is it only giving us 1.79 speed up instead of 2? There's some startup overhead here. Now we had to read in the file and divide it into lines, so there's some extra sequential work that has to happen before we can start running in parallel. So that's what we can get full speed. So that's the PAR programming model that we use for just adding parallelism to idiomatic Haskell programs. So if you've written a Haskell program, typically you can add some parallelism to it using PAR. The granularity is explicit, it builds this sort of data flow graph, and the data dependencies are explicit. We're not saying how to schedule the work, so we're leaving everything else to the library, to the runtime system, to actually implement the parallelism. And in fact, you could look in this library, look at the implementation of PAR, and it just uses concurrency, it's just built on top of threads, and you can even change the scheduler and experiment with different schedulers. So that's quite nice. So next, I want to give you a little taste of the Accelerate programming model. So Accelerate is a library in Haskell that lets you do GPU programming. So GPU is a graphics processing unit that you find on sort of most graphics cards that are designed for gaming these days. They've got these high-end GPU processors with many, many threads. And they can do very, very fine-grained parallelism on lots of processors at the same time. But GPUs are not like CPUs. You can't program them in the same way. They don't have the same instruction set. And we can't run Haskell code directly on the GPU. What they can run is a very simplified programming language called, one of them is called CUDA, for example, and it's a very simplified C-like programming language. But what the Accelerate library in Haskell does is it raises the level that you program the GPU at to Haskell. It gives you a domain-specific language to program GPUs that you can use from Haskell. So that's a picture that I generated from my Mandelbrot set generator that I'm going to show you. So Mandelbrot set is a very parallel problem. You can calculate the colour of each pixel in the picture completely independently of all the others, so it's a very nice problem for doing in parallel. So the Mandelbrot set is generated using this equation. So it's on the complex plane, so Z is a complex number, and it's an iterative algorithm. So for each point in the complex plane, we take the current value, Zn, and we square it, and add C, which is the coordinates of that point in the complex plane. And that gives us the next value in this sequence. So we keep on iterating this function until it either diverges or it doesn't diverge. And if it diverges, that point is not in the set. And if it doesn't diverge, then that point is in the set. And typically you would sort of iterate this for a fixed number of iterations. And if it hasn't diverged by that point, then you declare it to be in the set. And depending on how many iterations it takes to diverge, you colour that point a different colour, so that's how you get this nice colour picture. So I'm going to show you how this equation is rendered into the accelerator library. You won't understand all the details, but I want to give you some flavour of how it looks. So next is the function that computes the next value of z. So next takes two arguments. It takes c, that's this c, and it takes z, which is the previous z. And the result is c plus some function that works on these special values that we're passing around here. And it's c plus z times z. So it looks exactly like the equation. But we're computing on not normal Haskell values here. We're computing on things called exp complex. So exp is a special wrapper that the accelerator library adds to values to. As a sort of abstract notion of a value that the accelerator library understands. So this delivers a complex value in accelerate. And so given next, we can define iter. So this is the iteration that happens on each point in the complex plane as we're building up the Mandelbrot set. So we have to keep track of not only the current value of z at each point, but also the number of iterations, because we need to know how many iterations it took for the point to diverge if it diverged. So that's why we've got here, this is the value c coming in. And this is the value z, which is the pair of floats, that's the complex, and int, which is the number of iterations. So we have to do a bit of futzing around with pairing and tripling and so on. Don't worry too much about that. Here's where we call next to get the new value of z. And then we do a conditional here. So this is squaring z and see whether the result is greater than 4, which means it diverged. If it has diverged, then we use the original z. Otherwise, we're going to use the new z, that's the two components of z there, and increase the iteration count by 1. So you might not understand all the details, but this is kind of giving you the idea that it looks very much like what you want to write, with a little bit of extra fluff around the edges. It's not too far from what you'd expect to write if we're just specifying the algorithm. So putting this together, the whole Mandelbrot set is defined by this function Mandelbrot here. So we have to do some iteration. Go is the function that iterates just once. So it takes the input, which is the array of z's and their iteration numbers, and delivers the new array. And does that by applying this zip-with function, calling iter. So this is applying iter to pairwise to each of the elements of this array and this array to deliver the new array. So given this thing, we have to iterate it a certain number of times according to how many iterations we want. And that's done just here. So iterate is an ordinary Haskell function that applies a function to an argument repeatedly over and over again and gives you an infinite list back. And this bang here takes the nth element of the list. So the iterate is giving you an infinite list, applying the function go once more each time down the list. And then we take the nth element, or the depth element, that has to give the final result. So these are just ordinary Haskell functions. So iterate, bang, bang, and so on, just ordinary Haskell functions. But then manipulating array computations in the accelerate library. And when accelerate runs this, it generates some code in sort of abstract CUDA representation. It then gets downloaded onto the GPU in your computer and run. And the results come back into the Haskell module. So it's all very magic, but it looks quite nice. So another programming model we have is called REPR, so REPR is for doing array programming. I'm not going to go into much detail about how REPR works, but one of the nice things about it is that you can do these compositional operations on arrays. So we can map functions over arrays and then do zip with pairwise applying functions to arrays. And underneath, inside the library, this is automatically fused so that it doesn't generate intermediate arrays. So you might think that each of these maps will generate an array that's then consumed by the zip with, but in fact it all gets fused away into a nice tight loop underneath. And it's quite close to C performance. So REPR is very nice for doing sort of numeric array type computations and get good performance. And it executes in parallel as well. So I've given you a flavour of a couple of the different programming models that we have in Haskell for doing parallel programming. Everything's deterministic, it's very important, so you always get the same results. We've got this compile model for doing ordinary Haskell type computations, REPR for doing high performance parallel arrays, Accelerate for doing GPU stuff, and there's also a bunch of others. So strategies are also aimed at doing ordinary Haskell computation. Data parallel Haskell is rather like the REPR library, but you can do nested parallel computations, and inside the library it sort of turns those nested parallel computations and flattens them out into a single parallel computation. And there's various other GPU libraries as well. So you can see that we're sort of building all these tools on top of the nice flexible Haskell infrastructure that we've got. So I want to talk about runtime system support. So any questions on programming models before I go on? So, in the runtime sort of underlies all this stuff. It makes it all work. But you don't have any control over the runtime system. So you really don't want it to be the case that you run your program that should be parallel, and it isn't parallel because something in the runtime system is holding it back. There's a bottleneck there or something. So we really want this stuff to just work. But one of the principles is that the user says how many cores they want to run the program, not the programmer. That's very important because it means you can take a program written for any number of cores and run it on your computer that has a different number of cores. So the runtime is supposed to schedule all this stuff across the cores that you have. And if you program in another language, in languages that have automatic memory management, and try to do parallel programming, you might have noticed that one of the things you have to optimize when writing a parallel program is avoiding memory allocation, because very often the garbage collector can't cope with programs that allocate lots and lots of memory. So we really like our programs to be able to allocate and still run in parallel. That turns out to be quite a hard problem. So three key ideas that I want to talk about. The lightweight threading in runtime system supports. There's support for profiling and parallel agency. So the runtime architecture looks a bit like this. Each of these hex is a Haskell execution context, which you should think of as a virtual core. So we create one of these for each of the cores that you want to run the program on. So you can choose how many hex you have. And then inside each of these hex, there are a number of Haskell threads. So the Haskell threads that the programmer creates are scheduled across the hex that the user says they want to use. So that gives us a lot of flexibility. It means the runtime system can move these threads around according to what kind of communication is going on and what the pattern of execution is. And it gives us lots of flexibility for improving performance. So we think it's important to have lightweight threads, because it means that if you're programming with threads, I haven't said much about programming with threads today, but of course lots of people do program with threads, and we'd like it to be the case that you can program with threads if you need to. So you don't have to worry about threads being far too expensive and not use them. Threads in Haskell are very cheap, context switching is very fast. So, and threads are not only used for doing concurrent programming, they're also used to implement these parallel programming models that we've seen already. So the basic model here is that we've got lots of lightweight threads scheduled across hex. So profiling, the runtime system supports lightweight profiling. That means that many of the events that are going on at runtime inside the execution generate events to a log file. So they're very, very fast, small binary events generated to a log file. And that's slurped up by this program called ThreadScope. So we can get some insight into not only what's going on in the program, but also what's going on in the runtime system. So it's given us lots of insight that's helped us improve performance. Some of the things that you might see if you're a parallel programmer, things like working balance. So we saw this earlier on where one thread was doing, so one of the tasks took much longer than the other task and we didn't manage to get full power with it. You might see something like a slow startup and shutdown, where the program takes a while to get up to full powers and then when it's finished doing its parallel work, it slowly tails off. Some of the tasks take a little bit longer than some of the others. So you'd really like to avoid this in both of these types of things if you can. But you can't avoid them if you can't see them, so the profiler really lets you get some insight into what's going on. So heavy GC activity is something that happens quite a lot in Haskell programs. And the orange bar underneath the green bar here is the GCs. They're happening so rapidly you can't see the individual ones, but you can tell there's not much real work going on because of the bar at the top here, which indicates the amount of actual execution that's going on. And in fact, here it's sort of bubbling up around one core when we've got 4 cores available. Most of those cores are being used for the branch logic.
What is GC?
Ah, sorry, yes. Can I answer that question in a minute?
Okay.
So I'm going to talk about GC in just a minute, so I don't want to preempt myself. So actually, let me jump to GC. Yeah. So GC is really the most important thing that the runtime system designer has to think about. And it's a big problem because if you go look at the GC literature, there's a couple of bibliographies online. It's vast and tremendously complex. And there's all these trade-offs that you have to worry about. And invariably, if you build your own GC, you want to do something slightly different to what everybody else has done before, because your particular circumstances have different kinds of trade-offs and so on. So it's been very hard for us to find the right way to do GC in Haskell. So some of the reasons for this are you've got this trade-off in GC where more space equals less time. So the more space typically you give the garbage collector. I haven't said what GC is, have I? Sorry. GC is the memory management, the automatic memory management of the system. So it's the system that reclaims memory that's not used anymore and returns it to the system for use. Okay, so if you give a garbage collector more space, that means usually the garbage collector has to do less work because it can use more of that space to allocate objects into, and those objects get to die before it has to reclaim the memory. So GC is usually a space-time trade-off. You give it more space and it takes less time. But we've got working in the opposite direction, caches. So caches typically say, if you fit within my bounds, I will make your program run faster. So we're trying to fit in the cache, but at the same time we're saying, well, we'd like to use more space because GC is cheaper. So there's these two factors working against each other. And furthermore, when you get to a multicore, caches become even more important because if you can work within the cache on each of your cores, you don't have to contend for the shared memory bus as you share amongst all the cores. So working within the cache is really important. So the kind of architecture that we arrived at in Haskell looks a bit like this, so this is quite simplified. In each of the hex, there's what's called a generation 0. This is a generational garbage collector, where objects are allocated into the memory in generation 0. And then the garbage collector runs. And anything that's still alive when the garbage collector runs is copied down into generation 1. And everything in generation 1 just stays here. So what this means is that we've got a shared heap, a local allocation. So each of these hex, the threads running on these hex, can allocate purely to local memory. And we really hope that these generation 0s are cache sized, because that means that we can allocate memory into the cache reclaim it very quickly, and then allocate again into the cache. And hopefully we will just recycle memory in the cache without it ever hitting the main memory at all. And indeed that works quite well. It means we can scale the garbage collector quite nicely when these programs are allocating very fast into the generation 0. So we had a couple of papers about this, ICMR8 and ICFPR9, where we describe this stop the world parallel garbage collector, where the main, so the important factor is really being careful about locality. So when you collect the data in this generation 0, you better be sure that it's the thread that was running on this head that last touched that data. And you don't move it out of the cache of the processor that it's currently on into the cache of a different processor, because that would just destroy the performance. So, a thread scope profile looking at the garbage collections looks something like this. So this is a program that's allocating really, really fast on 4 cores. And it's doing a garbage collection actually every roughly 10th of a millisecond. So these GCs are really happening very fast. But when you're doing GCs that fast, and we have to synchronize for every single GC. So every GC means a full synchronization across all the cores that the program's running on. We see these slightly ragged lines where the synchronization happens. So we're trying very, very hard to synchronize as fast as possible. But nevertheless, some of the cores are going to respond before the others. So there will be some kind of delay at these synchronization points. And what's worse is that if one of our cores happens to be contended for, so suppose you run another program on your 4-core machine at the same time, and it knocks out one of the threads that's running Haskell code, the rest of the cores running Haskell code can't do their GC until this core down here finally wakes up again from running whatever program it was running. So that causes a problem, because it means that just taking out one core can destroy the performance for the whole program. So we worked on a new garbage collector a year or so ago, called local heaps. So local heaps has the same overall structure, but now we can collect the generation 0s individually, independently of the others. The generation 1 is still a large shared heap, and that's still collected in parallel with stop the world. So this is a picture of the local heap collector running. So you can see that these minor collections here are slightly offset from each other because they don't have to be synchronized anymore. So that improved performance. This is sort of going back a long way to research into this particular type of garbage collector. So we had a slightly different twist on the idea, which was to use a technique called read barriers, which avoids copying too much data into the global. And the results that we got were something like this. So here's a bunch of parallel benchmarks in Haskell showing the speed up that we get against the number of cores on a 24-core machine. And we also went all the way to using 28 virtual cores on a 24-core machine just to see what would happen if we simulate some contention for some of those cores. So you see that the red line here is the new garbage collector and the blue line is the old garbage collector. So in several of these programs, the local heap collector performs slightly better. In one or two of them, it performs slightly worse because there's a trade-off between some extra copying that we have to do in order to be able to collect these local heaps individually. And we have to copy more data down to the global heap. So, once we've done this, we found that the implementation of this local heap collector was incredibly complex, and it didn't really deliver the kind of benefits that we were hoping for. And furthermore, it had some slightly pathological cases where if you had programs that really needed to share lots of data between the two cores, then they would have to do a lot of communication rather than sharing the memory directly, and that made the program run much slower. And moreover, it doesn't really solve the problem that we have, because we still have to do these global GCs, and we still have to synchronize for the global GCs. So if you look at the 28 core results, even though the local heap collector always wins at 28 cores, it still slows down relative to running 24 virtual cores on the 24-core machine. So what we'd really like is to have no slowdown at all. And some of these benchmarks slow down quite a lot. So we've been thinking about other solutions to this problem. So one solution is to dynamically change the number of cores that the program is using as it runs. So the runtime system supports changing the number of cores at runtime. You can even do it from the program. You call a function that says, I want to reduce the number of cores to 4 when I was running out previously. So here's a program that's doing that. It's a program that, it's a parallel program, and it's it's got a separate thread running that's periodically changing the number of cores from 1 up to 8, and then from 8 down to 1 again. Doing that over and over again. And sort of demonstrating that we can change the number of cores and still run our programs as parallel. Because the parallel program is independent of the number of cores. So if we could do that dynamically in response to perhaps contentions happening on the machine, we can solve some of these problems of contention slowing down the runtime. So that's one direction that we can take this. So I'm getting near to the end. I want to offer a few conclusions about how purity helps in the parallelism. So obviously there's fewer pitfalls for the program. So when you're writing in a pure language, you can guarantee that each of the sub-expressions in your program doesn't interact with the other sub-expressions in the program. So that makes it much nicer to write parallel programs in. But one of the things that people often ask, me and other people who work on Haskell, is why can't you do automatic parallelization? So your programming language is completely pure. Surely you can automatically run all of those expressions in your program in parallel. And indeed you could do that. There's lots of research done 20 years or so ago that showed that yes, you could do it, but in fact most of the time it doesn't work because many of the expressions in the program are too small to be worth the cost of firing a parallel task to create a parallelism. So identifying the granularity is really the hard problem, and you can't do that in German. So this is really still perhaps an untapped resource, but actually quite a difficult resource to tackle. So it's not clear that we can do this. But immutable data structures really are very nice. If you had immutable data structures everywhere, it really makes your life a lot easier. So this reminds me of something that somebody at Microsoft said to me while I was there. There's a problem in Word where if you print a file and the printer doesn't respond, you can't edit the document until the printer responds. And to somebody who's a functional programmer, that doesn't make any sense at all, because surely the document is an immutable thing, and the printer would just have a copy of it. But no, the printer has the same document, and you can't edit it until the printer's finished. So immutable data structures, we should just be using them by default. Immutable data, it turns out, is much easier for a garbage collector to deal with as well. So that's very nice. But then all this purity and laziness and abstraction that Haskell has sometimes makes things a bit difficult. So in languages, in programming models like REPL, which give you a high level of abstraction but still want to get close to the C performance, they've got to cut through all these layers of abstraction and make sure it's compiling down to exactly the code that you want. And doing that sometimes can be quite difficult. Furthermore, lazy evaluation turns into mutation in the garbage collector. So quite paradoxically, you get a problem with too much mutation, which makes GC difficult. So, looking forward a little bit, we've got this shared heap system that works very nicely, but it's only going to work for a small number of cores. And we're only going to be able to do this to 8 or 16 cores perhaps, before we really run into scaling bottlenecks. But it's surprising that it works as well as it does. And what do we do beyond that? Well, we're thinking at the moment about doing inter-process communication in sort of Erlang style, where you do separate processes communicating via message passing. So if you had a system with 32 cores, you could have 4 Haskell processes, each running on 8 cores, communicating via message passing. So I think that's the right way to scale the system up to more cores. We have to deal with things like NUMA, non-uniform memory architecture. So many large multicore machines these days have memory distributed around the machine. So some of the memory is local to some of the cores. And if you want to access memory on a different core, then it costs more than accessing memory on the local core. So we haven't yet addressed that problem in the runtime system. That's what we're working on. And we like to do something around pause time. So the garbage collector, sometimes, if you've got a large heap, we'll pause for a second or two in a complete collection. So that's something else we need to tackle. That's the end of the talk. Thank you very much for your attention. Any questions?
Right, possibly a question from me. You talked about the possibility of, well, the unproven possibility of automatically parallelizing Haskell code. Has there been any research or thought being spent on automatically instead detecting parts of the code which could be offloaded onto the GPU?
Not as far as I know, so that's quite difficult because the GPU can only handle certain types of very specialised computation. So that's why we give you a DSL that you can only write GPU compatible code in. So I think if you were to automatically detect GPU code, it would be far too easy to accidentally do something that couldn't be run on the GPU.
I'm just thinking that this seems like the sort of thing that might be much easier to implement via a type system than actually detecting the correct amount of granularity and parallelizing code.
Sure, yeah, type systems absolutely. I mean, that's how Accelerate works. It gives you a type system that guarantees that your program runs on the GPU. So it's a slightly obscure type system. I taught Accelerate to some students last year in a summer school, and the problem they had was that they couldn't get their programs to type check. Once they did type check, they worked. That's often the problem we have with type systems.
Does Accelerate work on a CPU if there's no GPU?
Yes, it does. It has a simulator.
You mentioned that all of the parallelization methods were completely deterministic. You mentioned that the power library runs on the basis of the concurrency. What sort of mechanism does it use to make it deterministic if it's running in threads? Does there need to be some sort of way to sort of break contention if you were trying to put into the same IVAR twice?
Right, so what I didn't mention is that putting into the same IVAR twice is an error.
Alright, so it's just not allowed.
Yeah. So, yes, one thing we have to do is to ensure that it always runs all of the fault computations, just in case there happens to be a double put in there somewhere. That's how it guarantees to be deterministic.
Much simpler question here. You mentioned threading substantially. Haskell uses green threads, does it not? Are the hex the ones that are spread over processes?
So,
Or are the hex the ones that are spread over cores? Or what's the unit spread over cores?
there's one hex per core.
Okay, so then once again, thank you very much.